IndustRE project, there's also a part foreseen on implementation tools. And that's what I'd like to introduce to you today. The official title is way too complicated. I made a subtitle, which I hope is a bit easy to understand. Demand-side flexibility, business case estimation made easy. It's a bit of a bold title, a bit of a challenging title. We know that estimating the value of flexibility is not always that easy, and we tried at least in this project to make a methodology which makes it a bit simpler. You can judge yourself during the presentation and later and comment on it later on whether we succeeded in that or not. The point of the
yeah. So first let me should be working now.
Good. A quick outline of what I am going to talk about. That is, how do you calculate a business demand response business case? How did we do it till now? I'm going to try to explain you why there is really a need for a simplified approach. I'm going to guide you step by step through the simplified methodology as we developed it in the project. A nice example on on-site renewable energy business case, and then some conclusions and further steps. I know my presentation is a bit at the long side, so Fernando, start cutting me if needed. I know where I can skip a bit at the end of the presentation. Okay. Good. Calculating a demand response business case is basically combining quite a lot of input. The first thing is, which business model are you going to start from? Fortunately, my colleagues from Comias did already a lot of work in the beginning of the project to line out which the main business models are, which work in the different target countries. The naming we hear is a tiny bit different. We simplified it a bit further because we have to get it all fitted in one tool. But the main ones you'll recognize. The standard contract optimization is the time of use thing, the day-ahead optimization, reserve capacity, imbalance optimization, and on-site variable renewable energy optimization. These have been explained by Pablo earlier this afternoon. So that are the business models. A second thing is regulation. It's already said quite a couple of times today. There's quite a difference from country to country. Also there, the colleagues from Comias did a good job. In the graph here, what you see is per business model and per country, more or less the conclusions of the first work which has been done is summarized. So the green one means it works today, the red one means it's just a regulatory impossible, and yellow, well, that's a bit in between. It depends a bit how you interpret it. There are possibilities, but it is not like a major business model, let's say. That's the starting point. What you have to add to it is price information. If you want to calculate a business model, I have to have prices where I can start from. And we categorize them in the project in three categories. The green ones are the good ones. That's basically publicly available price information. For example, network charges, day-ahead prices, historical day-ahead prices you can download from the website. So that's the easy bit. Then you have the red ones. The red ones are quite often important when you calculate a business case, but they're typically hidden behind bilateral contracts. Let me take the example of the variable renewable business case. You can buy electricity directly from a wind turbine, but you're never going to find on a website for what price. It's just bilaterally negotiated between the wind turbine investor and the industry who buys the electricity. So does that mean that we can't calculate a business case? Yes, sure, we can calculate a business case, but we have to sit around the table and really talk about the contract details in order to calculate the business cases. It does mean, however, the drawback, however, is that we cannot draw general conclusions, like in general, in that country, that business case works very well because we don't have that bilateral individual contracts on the table today. And the orange ones are a bit in between. That means that within the consortium, we have a quite good feeling of what are the real market prices which are going on in these bilateral contracts, although they are not public. That's the third thing, market data. And then the fourth thing you need is a flexibility model. So you have to go to an industrial estate. You have to have a site survey with the technical people, with the energy manager, and you have to convert that somehow in a model where we can start doing calculations with. I'm not going into the details today, but that's sometimes quite a cumbersome job to get done. Good. Then you bring everything together. And what we try to do in the project as well is like we try to limit the number of ways how to calculate a business case. That's what we call business case calculation methods. So for example, whether I calculate a time of use optimization in France or I calculate a day ahead optimization in Spain, we can calculate that with the same optimization method. You have a variable price profile, you have a P component, maybe which is there in the network charges, but the calculation basically is the same. So we categorized also, we defined a couple of calculation methods. So what you see is that we really in a structural way over the different target countries try to get all the information in place you need to calculate the demand response business cases. Good. Why would we need something more simple than that? Well, there is one annoying thing, that's that flexibility model. What we see in practice, you know, as Vito Energyville, we have been doing this kind of surveys, I think, now for more than 6 years. And what we see in practice is that the skills you need to build that model are quite diverse. In the first step, when you have to go on site, you have to do that site survey, you have to do the technical installations, you need a broad insight in how plants work, how the energy flows go through that plant. So that's one type of skill you need. The second skill you need is like you have to transfer that into a mathematical model, which you can put in later on in your optimization tool. And what we see in practice, that's not so obvious to combine that. The business case calculation complexity varies as well. There are a couple of business cases which you can calculate on the back of an envelope, but there are not a lot where it is that easy. Some business cases you still can do with your Excel sheet, and I'm always amazed to see people what they can do with Excel. I'm not an Excel guru, but even these people admit that at some point it gets really, really tricky. And the most business cases you need like quite specialized optimization software. I put a couple of brand names down there, and you know, while the first two tools, like the calculator and the Excel sheet, well, they're quite in the skill set of many people, these optimization tools, that's a bit trickier. And then there's a third thing, and that's for me a quite important one, that is that building up interest in demand response is for many companies a long time. It's a time-consuming process, which takes what I typically see years from the first seed you plant to they are really going to do something with it. That can take quite a time. So for me, it is important to have a tool, a simplified tool, which in order of magnitude can estimate the value. The accuracy is in the first stage when the seed is still, let's say, in the premature stage, that the accuracy of that value is not that important yet. But that number is very important for the early adopters in a company to go walk around in the company. You see, this could be the potential of the value of what we can do with it. And then the seed can growing, and step by step you can get further. So especially for that reason, in these companies where you're still in that premature phase, it is important that you have a cheap, efficient methodology which gives you an order of magnitude estimation. Good. Requirements for a simplified tool. I already said that I think 5 times by now. Being cost effective and time efficient. Order of magnitude accuracy is good enough. And the third thing is, it is very important that you don't need that specific modeling and optimization knowledge. We try to avoid that. How are we going to do that then? A very naive approach could be, okay, you do lots of these demand response audits, surveys, you put them all in a database, And at some point, you had enough. You did enough. You know, you get a new customer, and this one comes close to that one. You pick that one out. That's your business case. You know, it sounds very naive. I know that, but one advantage you have here heard is I don't need these optimization tools. I can just pick out of a database the thing which comes the closest to what I want. And it's that principle you're going to try to achieve, but then in a bit smarter way. The approach we are presenting is an approach in 4 steps. They are called mapping, normalization, selecting, and scaling. You don't know yet what that means, but that will come step by step when I explain it to you. The first one is the mapping step. I've drawn here like a very, very simplistic way of thinking about the battery. You can see at the battery as a box of energy. You put power in, and the energy level increases. You take power out, and the energy level decreases. Very simplistic. And you can mathematically describe that very easily. This could be a part of an industrial process. At the left-hand side here, you see a part of a production plant which you put power in, it produces some products, I don't know what it is, cookies or polypropylene pellets or whatever. It goes in a buffer, and then you have a second part of the process here. If you think carefully about it, whether you have a buffer or you have a battery, in both cases, if you make a bit of abstraction of it, it's both just an energy buffer. I'm not going to explain it in the details now, but if you look in the deliverable you've written about it, you can mathematically prove that if you make some simplifications, this maps perfectly well on each other. Another example, which you can map on that same generic battery model, is, for example, it's CHP with a hot water tank. If you make abstraction of the losses of the tank, that tank still basically is an energy buffer. So that's the first step you want to do is, instead of doing that complicated modeling step, you make generic reference models, and you try to see which part of your process maps on these reference models. The second step is normalization. I put a very silly, simple example here. If you have calculated the business case for your car battery for trading electricity on the day-ahead market, you'll come to the conclusion that you can make more or less 20 euro per year by selling to the grid when it is expensive and buying when it is cheap. If I now have 20 batteries, I don't have to calculate that business case again. It just scales. If with 20 batteries, I can just make 20 times more money. So that's a scaling rule which simplifies the number of business cases I have to put in my database. That applies to prices as well. For example, if I have a time of use business case and the price difference between the night tariff and the day tariff is 15 euro and I can make 2,000 euro a year with it, yeah, if the price difference doubles, I can make the double amount of money. So by thinking carefully of these scaling rules, you can avoid a lot of pre-calculated business cases. 3 is the selection step. That's a bit trickier to explain. I'll come back later to it why I called it the selection step. I'm going to introduce you quickly to day-ahead optimization in a single slide. At the top here, you see the varying day-ahead price of some day, I think in 2015. You see the price is low in the night, about 15 euro. And typically at 5 o'clock in the afternoon, you have the highest price, in this case about 70 euro. And the trick, of course, is if I have that generic reference battery model, is to buy electricity when it is cheap and to sell electricity when it is expensive. And of course, that has to be within the constraints of my battery. I cannot exceed the maximum charge in my battery. I can't go below 0. And the second thing is, I don't want to trick you. I am starting with a half-full battery, and I stop with a half-full battery. So I didn't trick you by just draining down my battery. If you do this, for 1 megawatt hour battery, which you can put 1 megawatt power in, and you can get 1 megawatt of power you can get out, you can calculate an optimizer can calculate for you, that's better said, in this case you still could do it by hand maybe, that you can make a profit of about 66 euro. If you do the same exercise, on historical data of 2015, you could have made 19,000 euro per year. But I like to express it in another value. Instead of expressing it in euro per year, I love expressing it in euro per megawatt per hour. Why? Because then you have prices you can compare very well with, for example, what you find on the website of Elia. Elia, you know more or less what they offer for reserves. By expressing it in the same way, you can make easy comparisons between the different business cases. You see also in the unit that I added the megawatt here. That's because we do this calculation in a normalized way. So if I would have done this calculation for a 2 megawatt hour battery, this would have been 2.2 euro per hour. So this is the normalized price in megawatt per hour, euro per megawatt per hour. Good. Some properties, however, don't scale very well. And that's why we put them in a graph. I give you an example here. If I only double the battery size, but I don't double the power I can put in the battery and source out of the battery, unfortunately, my value does not increase from 2.2 to 4.4, but only to 3.68. That's not a big deal, because we can still make a nice graph of it. So basically what you do, you start with a very small battery here, very, very small, 200 megawatt hour battery there, and you put it all in a graph. So that's where the select step comes from. Basically, in your business case, you came to the conclusion, yeah, we have a process which maps on a battery with, for example, a 10 megawatt hour battery size. I take my graph, look up, and the price you would get for it is about 7.3, 7.5 euro per megawatt per hour. No optimization needed at all. And the last step is, of course, scaling back. This exercise, we build it in a normalized world. We have normalized everything to 1 megawatt hour, and so on. So the trick again, if you have 20 batteries, of course, you have to multiply with the according number. So to summarize, you start from an industrial process. You map it on a reference process, and for all these then in the reference process you normalize. Then for these reference processes, we have a database of these normalized business case graphs, as we call them in the project. So for all the reference processes and for all the different business cases, and I should have added a third axis for the different target countries, you have these graphs there. You pick out the right graph, you pick out the right point which you need, and you have your normalized business case, and you scale it back to the real values, and you're there. Good. This maybe makes sense for a day-ahead market optimization, but I see you thinking like, yeah, is that going to work for a variable renewable energy approach? That's the reason why I added this example in the presentation as well. We consider the case, which is profitable in Belgium, unfortunately not in every target country, where you have a wind turbine connected to an industrial estate behind the meter. And what's the nice thing about it? In Belgium, you can avoid quite a couple of, you can avoid the distribution and the transmission grid charges. You can avoid quite some levies. So that makes that you can buy electricity directly from that wind turbine at a lower price than when you have to buy it from the grid. For the graphs I'm going to show you, I assumed, it's an assumption, that we had more or less a price of 40 euro per megawatt hour from the wind turbine and 100 euro per megawatt hour from the grid. But here as well, scaling rules apply. So if the price difference changes from 60 to something else, we just scale our graph a bit. So it's just an example, don't focus too much on the number itself. Okay. Another thing, so the way you make profit is basically by, from a flexibility point of view, is that at the moment that there is excess wind, when you have to feed into the grid, you try to store as much energy as you can in your plant, and at the moment that there is not a lot of wind, then you, of course, you try to limit to buy from the grid. how does our reference model, generic battery model, fit in it? What we assumed is that generic battery model again, but on top of a fixed load. And the fixed load is a very important factor in this business case, as we noticed before. For example, we are going to look for this inflexible load. For example, there's a constant load of, for example, 0.5 megawatt, and then you use this battery and see how it all financially works. What you get if you get a graph which looks very similar to what we've seen before. So you have a changing battery size. This is the value you can get. This is for a fixed load of 0.1 megawatt normalized. And you see at some point when your battery is getting too big, yeah, it doesn't make sense anymore to make the battery bigger. Your business case is more or less finished. If you increase the fixed load, you see, you get a very similar graph, but it is a bit higher, so you can make a bit more profit. The next one, 0.3. And now the funny thing comes. At first instance, you might think it stays increasing. No, it is not. So at some point, you see it starts dropping again. So from the 0.4, I'm going back, the 0.4 case, it drops a bit. The 0.75, you're nearly at the bottom. And at 1 megawatt, it's finished. You can't make any profit anymore. Intuitively, this makes sense. At some point, when you're a very, very big energy consumer, which can source all the electricity from the wind turbine, you cannot make money with your flexibility anymore, because at any time you can just source all that renewable energy. And that gives quite an interesting graph if you mix the axes a little bit. So instead of putting here the battery size is on the x-axis, and I did that for different fixed loads, I turn it around here. So I put the fixed load on the x-axis, and I did that for different battery sizes. And you see that you can find optimal cases where the amount of renewable energy in combination with the typical load of the plant results in business cases for the flexibility. Okay, be careful. The business case for flexibility is optimal, typically around 0.3% of the fixed load. Good. Some conclusions. These were my initial requirements. Being cost effective and time efficient, order of magnitude estimate is good enough, and no specific modeling and optimization knowledge and tools needed. The third one, I think I convinced you of. I think I convinced you that without using any tool, I could show you a business case on a simple graph. The other two, there we make the assumption that if that collection of reference processes is good enough that you can do that mapping, which is representative, this approach can work. And I see you thinking straight away like, yeah, come on. In my industrial plant, it's rather complicated. You're not going to get away with it, like just to assume that my whole industrial estate is just like comparable to a simple battery model. And you're absolutely right. Most plants are way more complicated. Why do we think that this approach is still valuable? Because what you can do is, suppose I try to make a little sketch here of a typical setup in a plant where you have processes which are all connected. And like, for example, process number 4 has flexibility and process number 6 has flexibility. And the other ones just connect it all together. What you can easily show with this approach is that suppose that I would calculate a business case for process 4, assuming that it could operate independently. That's the business case value for process number 4. And I do the same thing for process number 6, that the sum of the two will be higher than the real business case. So if you would calculate the real business case, I can assure you that the value will never be higher than the sum. And that's still very valuable information, because what I've seen in practice is that lots of industrial people who set the first step in the direction of demand response, their expectations are more or less there. I'm going to get rich just for trading a bit of my flexibility. and their threshold to do something really about it is somewhere there. If I can prove with my simplified methodology that the value is somewhere there, then I still could teach them that it is still a bit too early for them to make that move. Good. Next steps with the methodology. Till now, it was paperwork. No, paperwork, that's exaggerated. Computer work. We have done lots of simulations to see whether it works a bit. We're going to test it real life in a number of case studies. These case studies will take place from now on, more or less, till mid-2017. We're going to try to target the different industries and the 6 different target countries in our project. And also an important element in the project is that we are going to try to take this methodology to the market. You know, market uptake is more and more important in these European projects. So we are looking at this moment for parties who are interested in this approach. We already had a webinar to look for the first interest, and later on in the year we have a full hands-on workshop with interested parties who want to get going with this. And if you're interested with it, you can find me or Dan or Stephen. And that was about it.
Thank you, Jeff. Okay, we open the floor for questions. So please feel free to. Yes, please.
I'm Chris from SAPI, and we are already involved a couple of years in demand-side flexibility. And the problem I'm facing is we are working with an aggregator. Yeah. For instance, I have 3 aggregators. One is offering me 10 euros per megawatt per hour, another one 11, and a third one 12.
Yeah.
Which one to choose? You might say choose the 12. But it is still a tendering process, and maybe in the end, the one who's offering me 12, he didn't succeed with Elia, and maybe I should have chosen the one with 10 euros, but maybe it was the most realistic
I fully understand your
offer.
issue. Yeah.
So, how to solve this enigma?
I cannot solve that for you, unfortunately. The only thing what we can do in the tool is, what we do is like, we look to historical data. And based on historical data, we do these calculations. Where the tool can help you is, based on historical data, look what the real value on the market would have been. So you can guess more or less which margin your aggregator takes on it. So and then you can estimate your risk a bit better, where you stand. You know, for example, the one who is 12 and actually the market price is only, I don't know, is significant, is just a tiny bit above that or just around that, then you know that you take a bigger risk. So in that perspective, I have to always be careful, because you know, I can't look in the future with this tool. You know, it's based on historical data that we try to do these estimations. I hope that answers your question.
I also have a question because of the historical data you use to do your calculations. Yeah. In hindsight, it's always easy to say when the price was low, when the price was high. So buying and selling is always perfect.
Yeah, yeah.
How can you avoid this in this tool as an industrial or whoever calculates this, that you don't fall in this trap? And how can you mitigate this? Is there something built in your methodology, or is there some?
Well, I think it depends a bit from your business case. For some business cases, for example, if you do a time of use calculation, day-ahead market trading, that's still quite predictable. And you know, well, I show you that on average during the day the price is higher than during the night. You know, there is still some predictability in it, which we do. Let's say we calculate the value, the maximum value you could have achieved. And then you can, based on experience, put a percentage on it, like we assume that this is realistic. For day ahead, that's still quite doable. If you go from imbalance, I agree, then it gets really, really tricky. Yeah. But for example, to add to that, because we had quite some focus on the last business case, so the on-site VRE case, there again, based on wind predictions, which are getting better and better and better, I won't say that the value which comes out of the tool is what you really can make, but it is not like only 10% of it. It will be rather in the order of magnitude 80–85% of it.
reactions? Please.
I have a question related to the normalization or standardization of processes.
Yeah.
How many of them have you already identified? Is the battery is kind
Yeah.
of general one?
Honestly, I think that we are gonna get away with 2, maximum 3. The battery model, I think we definitely need something for schedulable load. And then I have to think already very deep to find another one. Maybe kind of process which has losses, like some storage with losses. But if you have these 3, you already get quite an end, in my opinion. And if you have feedback on it and say, I missed one of them, then give me some feedback on it. But I think with 3 we will get quite an end.
I think there is a lot of appetite for putting a value on the flexibility on the industrial side, but also growing appetite in the residential and commercial sectors. Which of the processes you have identified in the model is closer to the energy profile of a commercial or a residential consumer, and is it easy to adopt it somehow, to adopt the model also to have like implementation on that?
One of the business models I see coming for residential is car charging. For example, your battery, and it's more or less there. Of course, there's an availability of that car battery, which is not 100% of the time there, but that's definitely an opportunity we start seeing. Further, what you can do as well is like if you go like to heat pumps and you start using your house as a heat buffer, there are definitely possibilities as well. I think for large buildings, definitely there are possibilities to adopt this approach as well. For residential at the lowest level, we have to be maybe a bit careful or look into it.